Spread, ladies and gentlemen, thanks for joining us today. A smaller crowd than usual, but that's okay, maybe because supportability isn't as sexy as some of the other topics like Weibel. And yes, I did infer that Weibel is sexy. But what is supportability and how does it relate to reliability? So before we launch into this topic, let's go to an example, a real world example, a case study where this armored personnel carrier, it's quite literally what its name suggests, an armored personnel carrier. It's designed to carry personnel across a battle space, and it's armored, so it offers protection. You can see that it has tracks that helps it with mobility, doesn't have to be on roads. And these armored personnel carriers or vehicles like this have been the mainstay of many battles in the military or 20th century military campaigns. And this one was actually subjected to a midlife modification or midlife upgrade, whatever you want to call it, maybe midlife crisis, because it was getting pretty old. And these vehicles are often used for decades before they get replaced. And in this case, there was a belly plate, or what we called a belly plate on this armored personnel carrier on the original version, to allow maintainers to access the underside of the power pack, which is very useful if you wanted to do things like drain oil. But in the midlife upgrade, they decided to weld shut this belly plate to protect against chemical agents and IEDs and everything else. Even if you have a plate which is bolted together, the fact that it has a discontinuity in the structure is a structural weakness that IEDs can support. Problem with that, though, is that how do we go about changing the oil? Now we have a belly plate welded up. Well, in this case, you have to remove the power pack to change the oil. The reason being is because I didn't think to include an oil pump in the midlife upgrade. So just a rhetorical question, if you had to classify or rate the supportability of this vehicle, what would it be? And I know we're talking about a very specific instance, a very specific functional characteristic. The reality is this vehicle is now a lot less supportable because it is that much harder to change the oil. And not only is it harder to change the oil, when you get a crane overhead to remove the entire power pack to change the oil, you do all sorts of damage to that power pack. The power pack is designed to be inserted and replaced very infrequently. It's supposed to happen, but it's not supposed to be a weekly occurrence for obvious reasons. But it borderline became that approach because we needed to change the oil on these big engines quite frequently, as you can imagine. Of course, that means you need to have cranes, you need to have more maintainers, in addition to all the damage you're causing on the power pack when you remove it and replace it. Now, this whole concept of supportability is linked to what we call life cycle costs for these sorts of things. And this is a chart from the Defense Acquisition University from the US. It's a little bit dated now, but the actual principle is remarkably consistent. And you can see on this chart, we have on the vertical axis, life cycle costs of what are usually military acquisitions or military projects. And as you can see, the life cycle costs for a particular capability increases over time. This is a cumulative line, and you can see how that line starts to get steeper and steeper once we move into the sustainment space, the operations and support space. So about 60 to 80% of life cycle costing, which is a very military term, I know, will be spent during sustainment. But anyone who comes from an asset management background or comes from a fleet management background will know this to be true. You spend most of your money supporting your fleet. You spend most of your money repairing failures and et cetera, et cetera, et cetera. And of course, we can often get wowed by the purchase price of things, but it's usually in sustainment phase, the operations phase, the support phase, where the fuel, the oils, the maintenance, and everything else, those costs dwarf the purchase costs. But the problem with that is that the ability to influence lifecycle costs decreases rapidly from conception to manufacture. So of course, your ability to influence lifecycle costs is almost is as high as it's going to be at the very start of your design process. But they found for these military projects that 90% of our ability to influence lifecycle costs is used up by that particular point where we transition from what the military US DoD calls engineering and manufacturing development through to production and deployment. In the real world, we call that essentially transition to manufacturing, transition to production, whatever you want to call it in your own space. But we stop designing, we start building. By that stage, 90% of our ability to influence lifecycle costs is used up. But it is often the case that this is when we start thinking about lifecycle costs. We'll have bright young design engineers say, hey, for this new military vehicle we are about to design, we have to focus on speed and protection and firepower and capacity. These are the most important functions. And of course, we need to build those into our machines. And we'll worry about supportability later on. I mean, that happens secondarily. The problem with that is that we often get tunnel vision and we forget about it until it's too late to do anything meaningful about it. And when we do have that workshop where we come up with wonderful supportability ideas, then it is often far too expensive to implement the corrective actions or the great ideas. Now, what is supportability in this context? Reality is no one has a widely accepted definition. It's just the ability to support, and essentially it can be measured in many things, but perhaps the most common way of measuring supportability is how much it costs to keep your thing up and running. The reality is we forget about it until it's too late. And because a good chunk of our operations, management, or our sustainment costs come from repair and maintenance, supportability is tied at the hip to concepts like reliability. So you can't ever think about one without thinking about the other. Now, for veterans of my webinars, you'll have seen something like this over the years, which is sort of supposed to be a generic production life cycle or product life cycle or design life cycle, whatever you want to call it. And you can see here that I have incorporated into this life cycle where you can see you've got concept specifications. In the middle, we have this reliability design cycle, which is a subject of lots of other stuff I've done through Ascendo. And then we move on to manufacture, sustainment, and disposal. The reality is most people who use the term supportability do so from most people who use the term supportability come from organizations where they use activities like FMEAs to get their products to where they want them to be. So let's just recap on how FMEAs influence our life cycle. Now, the system FMEA is there to identify the vital few component functional failure modes for our design FMEAs to focus on design corrective actions. And our design FMEAs are there, amongst other things, to help us identify the vital few manufacturing specifications that our process FMEAs are going to address. So we want to do system FMEAs before we start designing to improve, prioritize effort. Design FMEAs get done on a fraction of our overall system to improve the design, including the interfaces between components. And last but not least, our process FMEA is based on, as opposed to looking at the product, it looks at the process. And the process has failed when the product it produces is outside of specifications or otherwise not high quality. And so these three different sorts of FMEAs work very closely to make sure we get something which is amazing for our customers, our users, our operators, our soldiers, sailors, and airmen. At the very start, we need to think about supportability. What does this look like for the user and customer? And for those of us who are still struggling to grasp what supportability is, join the club, but we're going to go through a couple of examples which hopefully puts the term supportability into real-world context. Now, supportability requirements need to outline what it looks like for the user and customer. Does your product need to give early warning of impending failure? Does your product need to align with a specified preventive maintenance regime of your plant? I.e., do you have weekly downtime, and therefore the product you're purchasing needs to have preventive maintenance intervals that align with your plant's weekly shutdown? Does your product, this is going to be a rhetorical question, does your product need to have the replaceable components, the parts that wear out and routinely get replaced? Do they need to be accessible, really accessible for your maintainers and technicians? And the answer is yes. Does your product or machine, do you want it to only have to, do you need your maintainers to only have one spanner or wrench in order to undo every single bolt? That's sort of a maintainability requirement, which is within the family of supportability, etc., etc., etc. Other things, does your product or machine need to communicate with your logistic information system over a Wi-Fi network, or use RFIDs to help transmit its location? What does health and usage monitoring systems mean to your product? Whatever your philosophy is as a customer, user, or operator, it needs to be embedded in the concept. Then when we come to specifications, we need to think about the functions that are incorporated into our design. So if your machine does need to communicate that it's about to fail, how does it do that? What communication protocols does it use? And the reality is, supportability happens very, very early. It happens right at the start. If it doesn't happen there, it's never going to. And so for that reason, many supportability efforts devolve into just calculating how much support your product needs to maintain. It's not there to influence supportability. It's there to deal with the actual supportability that has been created, and often in many cases throughout without ever thinking about it. So some organizations schedule supportability to happen right at the end when they start to think about production or maintenance. It's okay, we're transitioning, so let's get the maintenance plan up and running. But unfortunately, it's too late to make meaningful changes. Supportability needs to happen right at the very start when we're all excited about designing an amazing new product. So you can't easily at least make your system or item supportable after it has been designed. So let's go back to our armored personnel carrier, which is, like I said, the backbone of many militaries across the world. And you can see at the top of this armored personnel carrier, it actually has a weapon. It has a turret. Most people who think about turrets and weapons on armored vehicles think of tanks. And tanks aren't armored personnel carriers. Tanks carry very few people because they're all about having monstrous weapon systems, huge barrels, huge cannons up there, turrets that can turn and really lock onto a target and help the gunner who's inside the vehicle stay on their point of aim. But even smaller APCs like this still have formidable turrets and weapon systems. And in the heart of these armored personnel carriers and armored vehicles, you have what is called a turret positioning system, TPS. You can see here that we have at the very heart of our turret positioning system a turret ring. And that turret ring has got teeth on it that rotary gear drives can turn in order to turn the turret from left to right. And you can also see that there's this thing called the linear drive. Now, that doesn't make a lot of sense for people who haven't been exposed to this sort of machine. The linear drive pushes the barrel of the weapon up and down. You can see there's gyroscopes. So the turret positioning system essentially knows its pitch, roll, and yaw, or attitude, or depression, or how, when it's turning and things like that. You can then see that all these things get plugged into what's called motor controllers. And so what that essentially means is that the gunner who's interacting with this system with hand controllers can essentially have the barrel of the weapon pointing in exactly the same direction, regardless of whether the armored vehicle turns, goes over a bump, goes backwards, increases speed, slows speed down, etc., etc. These turret positioning systems are really, really good at making sure that barrel points out wherever that gunner wants this thing to aim, regardless of how many boulders the vehicle is traversing, and if the vehicle is turning to go around a tree or an obstacle or things like that. And so, question for you guys. If you were in charge of a brand new armored vehicle, which had a turret with a main weapon on it, and obviously that implies a turret positioning system, which helps the gunner make sure the barrel is pointing in the right direction, no matter what the vehicle is doing, what would you be looking for in terms of supportability from this turret positioning system? So if you've got any responses, any ideas, or any hard-earned experience in this regard, please feel free to share it in the chat window. This is brand new information. Feel free to sit back and let everybody else do the hard work. But that said, this is not, even though some of us might not have had a military background, it's just a machine that needs to do something and you need to maintain it. What would you be wanting from a machine in terms of helping you make it some more supportable? GPS calibration. So it needs to make sure that, for example, I'm guessing, Victor, that the GPS calibration, although that wasn't implied here, and not all turret positioning systems have GPS capabilities. Let's say it did. It needs to ideally calibrate automatically or let you know when it's not calibrated. Is that right? We'll wait for Victor to get back on that one. But in the meantime, I see Michael has put in there the periodicity of lubrication for the gears. If you need to lubricate the gears every 5 minutes, that's a less supportable design than one that only needs to be lubricated every year, for example. Richard points out, consider whether maintenance is performed in the field versus the shop. Fantastic. Many devices in military vehicles can be designed in a way that allows maintenance to be done quite happily in dusty, dirty environments under trees. If that thing needs to be repaired in a shop where the ground is perfectly level, the atmosphere is perfectly maintained, then that is inherently less supportable because that is harder to bring back online. Victor has clarified that. Fantastic. Defining life for different components. So we've got some really good answers here. Williams wrote report on motor loading to predict gear wear and lubrication. Fantastic. We're starting to think about what we might like. And the term residual useful life is used in this sort of scenario where the machine, the device is designed in a way where it can understand how much longer its components have before they fail. And then if they understand how long they've got to fail, I can see Asim wrote that in his or her, sorry, I'm not sure. My apologies. I'm not sure of who Asif is. Asim is, so I should say. But do we want the residual useful life to be communicated automatically, wirelessly? How do we get firmware updates installed on the software? What sort of maintenance gets conducted by untrained operators, i.e. in the field? Do you want to track its accuracy over its service life? Do you want a modular maintenance philosophy? So I can see that there's a couple more comments coming in, but we're all in the same mindset. How do we want this thing to be easier to look after? And if, depending on how you run your particular military, no worries, Asim, you might have a very specific approach. For example, modular maintenance is a maintenance philosophy where you ask designers to come up with machines where you can simply swap out components really easily and replace them, and then have that swapped out component taken back to a workshop to be repaired. That is one philosophy. And that sounds all well and good, but it comes at a cost. And that cost needs to be well understood, not just monetary cost, but if everything's modular, then it usually requires bigger machines, bulkier machines. You can't pack as many components into a smaller space as you used to. So modular maintenance, some organizations love it. Some organizations shy away from it. And there's no right or wrong answer. It's just the right answer for your organization. So when it comes to supportability, you have to start with the requirements, which is when I say what a requirement is, that is how a user or operator or customer would describe what they want the thing to do. Supportability function is how an engineer or designer would describe an element or characteristic of that design or that machine to support a requirement. A specification is a very, very clear definition of that function, which usually includes tolerances. And of course, that specification is often based on metrics. How long do we need servicing to? So how long should the servicing interval be, et cetera, et cetera, et cetera. Now, supportability function is a behavior, process, action, or task that enables supportability. One example function is the ability to predict failure. Can it warn about failure? Can it communicate information about failure? Can it diagnose failure? Is your system easy to rectify failure? Are the high usage components located in arm's reach, et cetera, et cetera? Can we prevent failure? Can we have fault isolation? Can we mitigate faults? And of course, when it comes to supportability, there is so much involved that it makes supportability a very challenging area to easily define. So this is a little map which shows just how many factors go into things like supportability. What you need to do when it does fail, corrective maintenance, so on and so forth. So when it comes to supportability, though, and reliability, there are two main metrics that sort of overlap, and that is reliability itself and availability. Now, when we talk about reliability and availability, but that implicitly includes a whole bunch of what we call maintenance or maintainability metrics as well. And so there are tons of metrics out there, and here are but some. If you we're not going to go through it in this conversation, but if you're into availability, you need to understand whether you want inherent availability or achieve availability. We've got built-in testing on the left. We call that BIT, or built-in testing equipment, BITE. So what is the built-in testing coverage, the built-in testing accuracy? How much of your machine do you want built-in testing to look at? And how accurate do the fault diagnoses be? And here's a hint. You really need to have a robust FMEA or robust fault tree analysis, or otherwise have a really good understanding of what the weak points of your system are before you can do that. So supportability is in a way necessarily a broad topic, and there's not a lot of agreement on it. So you need to work out what it means for your system or your organization, because it can mean all things to all people. Now, what supportability is not is support itself. We need to understand that supporting things can be expensive, but let's look at what I mean when I say supportability is not of itself support. Just see a couple of questions. Are you using the term supportability interchangeably with maintainability? No, I'm not, because although maintainability is a huge part of supportability, there are lots of different definitions of maintainability out there, but there's also some supportability metrics, or some supportability characteristics, I should say, which are not specifically linked to maintainability. So if you think about, you could argue that residual useful life is a good example of overlapping maintainability and supportability, but in reality, residual useful life is a reliability metric more than anything else. The ability to use that residual useful life, or the ability to calculate it and then use it to inform decisions. Yeah, one could argue that's maintainability. One could argue it's supportability. Another form of supportability is, for example, how much lubrication do you need to go through? How much fuel do you need to go through? Something can be awesome to maintain, but if it goes through a lot of fuel, if it goes through a lot of consumables or a lot of material like that, it's not as supportable as a comparable system, which doesn't. So for that reason, maintainability is not equal to supportability, but many aspects of maintainability overlap with supportability. Michael wrote, one question is, what is the indentured level of replaceable units? Now, that's a very specific question, but I think it's a rhetorical question. But essentially, I think you're getting at, where can you replace those units? Can you replace these units at the frontline units, frontline workshop, depot, whatever the right term is for your organization, or out in the field, or on site, or does it have to be sent back to the OEM, et cetera, et cetera. But let's look at this big truck here. This is a really big mining truck. When I say really big, I mean really, really big. And these trucks have a 400-ton payload, and they'll often be driven non-stop. Just so you know, for whatever reason, I cannot see the attendees anymore. I can just see that we have 19 of them. My window has gone completely blank. I might shut it and open it again to bring you guys back, but no, can't see a list of you guys there. Just so if you have any questions, feel free to put them in the chat window. I can see a couple coming up. I will get back to them before this conversation is done. So this big truck will often be driven non-stop. It costs, say, $5 to $6 million. So it's kind of a big deal. And in the middle of this big truck is a really big engine. And when I say really big engine, I mean really big engine. This engine is bigger than most vehicles. It is a 20-cylinder engine. It of itself costs between 700 to 800,000 US. And of course, we often need, or mining operators need to have plenty of spares on site, including engines, when their mining operation is, for example, in a far-flung corner of the world where access and ingress and egress is a challenging concept. So let's just say we are trying to work out how many spare engines do I need for a 3-year period for one truck. Now, before we rush to the textbooks to find the equation, what I want us to do, or what I want you guys to do, is understand, before you do anything else, including anything related to supportability, is understand, how does this thing break? Now, in previous webinars, I have introduced the tree of failure, where I have a bunch of questions that start at the top, go all the way down to the root cause and corrective action that help you work out what you need to do. So if something has failed, or you're trying to ponder how your system might fail, before you just say it has failed, you need to say, well, what is it doing or not doing that classifies that particular event as a failure. Once you've defined what your system is doing or not doing, then you ask some more questions. What does the broken bit look like? How did that thing break? What started it? Now, in the bottom is, we ask ourselves, what did we do wrong? And the answer to that question is essentially the root cause. The only thing you can change is your behavior. You cannot change the laws of physics. And the corrective action addresses the root cause, which is essentially, what do we need to do moving forward to either somehow mitigate this failure? Now, the bit in the middle, how did it break? The answer to that question is what we call a failure mechanism, the physical, chemical, electrical, thermal, other process which results in failure. And veterans of my webinars will have seen the random hand of failure that I use often to represent the many different factors and things and characteristics which introduce uncertainty into how long our thing lasts. You can see that I have a few up there, 4 different factors, but there's tons more than that. And frustratingly, what that will do is mean that seemingly identical components or machines will have different times to failure. You can see on the horizontal axis, we have 100 blue dots or circles representing the times to failure of 100 seemingly identical machines or components. And the frequency or the density of these data points is described by what we call a probability density function curve. Now, every random process, including failure, has this PDF curve. This characterizes the uncertainty in time to failure. And every different failure mechanism will have a very unique curve. It's shaped in a unique way because each failure mechanism is going to fail in a particularly unique way. Corrosion will have a different PDF curve when compared to fatigue, for example. But once we have a PDF curve, we can use the information encoded within this PDF curve to draw what we call a reliability curve. You can see here the reliability curve starts at 100% and goes down as our system gets used, and it will eventually hit 0 as our time to failure increases. Now, why is this important? Is because this is the PDF curve of a failure mechanism that has an increasing hazard rate, the rate at which a thing that is still working fails. And if we have an increasing hazard rate, that means our system is wearing out through failure mechanisms like diffusion or wear or oxidation or lubricant contamination. In fact, if you see a PDF curve which has a beautiful bell shape like this one, it is failing through failure mechanisms which has this additive wear out characteristic. That is, damage is accumulating proportionally to the use. And so there's tons of examples. So this is what one wear out failure mechanism looks like from the perspective of probability and statistics. And this just so happens to be the probability density function curve that describes the time to failure of our truck engines. The reason why that's important is because it is only wear out failure mechanisms that can be, for example, subjected to preventive maintenance or condition-based maintenance. Can anyone tell me why that is the case? Why is it that only wear out failure mechanisms can be subjected to preventive maintenance or condition-based maintenance? Anyone want to hazard a guess? So I think William writes, understanding the failure helps us extend the life of components, but for current state, we only care that engines fail at a rate. We need that many spare engines, whether it is cylinder wear or gear failure or timing belt breakage, out of service is out of service. I don't think that answers the question though. Karen's a lot closer because she writes that worsening or degradation can be detected ahead of failure. Without wear out, we cannot predict when the item will fail, says Victor, which is not entirely true. But Greg is on point. There is no value in proactively replacing a part with random failure. So all failure is random. I think we're getting close to the point, though. I like what Karen is saying, though, is that wear out implies the accumulation of damage. And so servicing or preventive maintenance, all that is the removal of damage. So if your failure mechanism is not based on the accumulation of damage, there is no point in doing preventive maintenance. Okay, yes, Greg, I understand. Greg points out there is no value in proactively replacing a part with constant failure rate. That's the point. You don't mitigate those parts where things wear out, where damage is accumulating. So condition-based maintenance, essentially, all that means is that when we say condition, we actually mean understanding how much damage exists. Think of a fatigue crack. The length of that crack is the amount of damage. When that crack hits a certain length, your thing fails. So because our thing is wearing out, that means we can do preventive maintenance and condition-based maintenance. Now, this PDF curve, this weird-looking one, which is more to the left, this is what it looks like when our system is wearing in, which is not our engine in this case. This is not particularly intuitive, but this is a PDF curve that sort of morphs away from our bell curve when we see wear-in or infant mortality failure, where we have a subpopulation which is defective. A defective subpopulation usually means manufacturing quality. It could often mean that we have training issues because it's not being installed correctly. It could also mean that we might need to have a burn-in regime where we try and expose those defects early. And this is Greg's constant failure rate, where this PDF curve, which is anchored on the vertical axis, the constant failure rate or constant hazard rate is all about things that are caused by randomly occurring external stresses that are catastrophic. So weather phenomena, voltage spikes through our electronic components. It doesn't matter how old or young a capacitor is. If it's going to be subjected to a 5,000 volt spike, it is going to have a bad day. So those sorts of failures, where they are caused by catastrophic external stresses, appear at a constant hazard rate, because it doesn't matter how old or young your system is, it's going to die. For tires, we associate vehicle tires as wearing out, and they do. But if they're failing due to puncture from spikes or debris on the road, doesn't matter how old or young your tire is, when it goes over that spike, it's going to fail. And so those failures, at least, would have a constant hazard rate. And most of our textbooks, unfortunately, focus on constant hazard rate. And why is that important? Well, it means that if we use the textbook approach, where we assume our engine has a constant hazard rate, then we'll get this prediction in terms of the number of failures our poor old truck's going to experience over 3 years, where we need to replace an engine. And so you can see here that there is a roughly 22% chance that our engine will not fail in 3 years, according to this textbook approach. There's about a 34% that there'll be only one failure in a 3-year period. There is a 25% chance that we'll have 2 failures in a 3-year period if we assume the thing has a constant hazard rate. And that means that if we want to be pretty sure that we have enough engines on site, i.e. 99.55% in this case, well, we need to have 5 engines, because all those bars add up to create a value of 99.55%. So long story short, if you want to be 99.55% certain that you have enough engines on site, you need to have 5 engines if you use the textbook approach, which assumes things don't wear out. I know. But if we use the right approach, where we actually understand how our engine fails, we know it's failing due to wear out, then doesn't have a constant hazard rate. And it turns out that the distribution of likely engine failures is very, very different. In this case, we only need 3 engines based on this presumption to be, it's not 100% certain, but it's so close to 100% that there are not enough decimal points. So that means that if you understand how your system fails better, you might, instead of having to take 5 engines to some far-flung corner of the world, you will only need to take 3. And that's obviously a big deal. Now, this is an example, an exercise, not in supportability, but in support or logistics. All we're doing is working at how many spare parts we need. And it just goes to show that you really need to understand how your thing is failing to do that. But better yet, we want to focus on designing a supportable or more supportable device. So we need even fewer engines again. Simply calculating how many failures are you going to experience to understand how many spare parts you need is not supportability. So let's go back to our armored personnel carrier, which has a turret positioning system, which we've already looked at with a bunch of different items. And let's just focus on one component, the rotary gear drives. And the rotary gear drives are the motors which turn the turret ring. Obviously, they're kind of a big deal. And so that means that if these things fail, our turret positioning system is done. And so our turret positioning system has 2 rotary gear drives. Now, during design or during a FMEA process, perhaps the fault tree analysis or whatever it is, one of our bright young engineers is concerned about the insulation breakdown due to moisture. What does that mean? What is insulation breakdown in an electric motor? Well, let's have a look at this particular phenomena that our bright young engineer is really concerned about. What does this mean and what happens when it occurs? Well, if we pull apart our electric motor, you can see there's tons of components, and I'm not going to go into a lot of detail about how electric motors work, but one of the key components is the stator, which essentially is over here on the, you can see it circled on the right, got lots of electric wires wound tightly around a drum or a cylinder. And what this means is that current is able to flow through our stator to create a magnetic field, which can then push against magnets. And that then essentially creates kinetic energy while allowing the shaft to rotate. But if the insulation on these cables break down, that means there are teeny tiny short circuits. So as opposed to the electrons traveling the full length of our winding, our cables, they only travel a part of the way before they jump across and leave our stator. And that's a problem, because if that happens, you need more electrical current to generate the same magnetic field, or more electrical power for the same mechanical output power. So, question for you guys. Is insulation breakdown a wear-out failure mechanism for our rotary gear drive shaft? Is it wear out? Yes, Michael says yes. Well done, Michael. And why is it wear out? Feel free to jump in again, Michael, if somebody else wants to. It is a gaining issue similar to wear out. I think William might mean aging. The reality is additive. So we're certainly, you're definitely getting there. Essentially what it means is that damage is accumulating. So any failure mechanism where damage accumulates, i.e. an older version is less likely to survive the day than a younger version, then we have wear out failure mechanisms. Corrosion, wear out, because the damage accumulates, the amount of oxidation gets more, increases every single day. Fatigue, wear out, the crack gets longer every single day. Lubricant contamination, wear out, because the amount of contaminants increases every single day. So if your thing is accumulating damage, then it is wearing out. Why is this important from a maintenance and supportability perspective? If you know that the main failure mechanism for this motor is insulation degradation and it is wear out, why is it important from the perspective of maintenance and supportability? Why is that important? We talked about this earlier today. There's some well-known maintenance activities that can only apply to failure mechanisms that wear out. It will fail if this effect is not anticipated. Well, that is true in a way. Well, actually, I wouldn't agree with that, Evan, because I can anticipate failure and it will still fail. So if I just anticipate failure, or the effect of it, doesn't preclude it from actually failing. Drives a number of spares required in maintenance time. That's true, but that applies to things that don't wear out as well. We better understand what activities are effective. Yes, it will be degrade, but it will likely be impractical to replace. So we're sort of dancing around the topics or the answer until we get to Greg, who says you would like to replace it before the failure occurs during emission. Perfect. If we have a failure mechanism that is accumulating damage, it gives us the opportunity to either replace or repair it or remove the damage, reset its life before it goes out on emission. It allows us to do preventive maintenance, servicing, or condition-based maintenance. We can only do preventive maintenance, servicing, or condition-based maintenance on things that wear out, things that accumulate damage. Couple of sort of rhetorical comments and questions. I need to pick apart, but we might move on because hopefully we got the point across that you can only do those sorts of activities on things that wear out. So before we do servicing intervals or preventive maintenance regimes, you need to understand how your thing is going to fail. And if you do understand how your thing is going to fail, then ask yourself, is it accumulating damage / wearing out? Now, how can you get early warning that insulation is starting to break down? Now, I'm going to share an answer to this question that when I run FAMICA courses, and one FAMICA course in particular where I had a bunch of students came up with a really cool way of detecting or generating early warning that insulation is starting to break down in our rotary gear drive. So, any ideas about how we could get early warning that insulation is starting to break down in our electric motor rotary gear drive? Monitor the electrical draw, increasing current draw, fantastic, drawing more current. Now, one thing that we're missing in that, which is very apt observation, is that one of the issues with turret positioning systems is that the current draw is inherently variable. The reason being is that if the turret needs to rotate slowly, it doesn't need a lot of current. If it's rotating very quickly, it needs a lot more current. So it's very difficult to inherently look at the peaks and troughs of current draw and then work out if there is more current being drawn for equivalent mechanical power outputs. Now, I can see that Michael is talking about doing an impedance test to look for turn shorts. Fantastic. So that involves some sort of inspection where you have you essentially measure the impedance of the electric motor. And we talk about rotation speed monitored by gyros versus inputs. Now, rotation speed won't be monitored by the gyros, William, because the gyros is all about it gives you the position and the attitude of the hull itself, which is separate to the turret. But we're getting closer. And let me share with you the corrective action that the team came up with for getting early warning for our rotary gear drive. Now, of course, you will have a machine or a computer which is hooked up to the rotary gear drive, which not only monitors current draw, it actually controls it. So we have the controlling software, the computer, which will control and of course then monitor how much current is being drawn. We also need to make sure that, for example, current draw will increase if there is some sort of lubrication issue, which is not necessarily related to insulation breakdown, or if for whatever reason it's just harder to rotate the turret. And so the team came up with the idea of having really inexpensive strain gauges embedded in the feet of the bracket holding the rotary gear drive. And what that allows you to do is understand very easily, well, if we know the torque that's being output, and of course we can easily monitor the rotational velocity as well, then we can compare the mechanical output, once we have the torque and the rotational angular velocity, and the amount of current being drawn, and we can monitor the relationship between input electrical power and output mechanical power. The really good thing about this is it seems funky and really next level space age stuff, but it's actually not. It's really simple. And these strain gauges are really easy to implement if you think about them early enough. And so this is an idea. This is just sort of brainstorming session you want people to go through when they're talking about condition-based maintenance and supportability and things like that. So a rhetorical question is, can predictive or condition-based maintenance, or how can we, what action can be implied, or might work for the rotary drive shaft, rotary gear drive shaft. All the words are stumbling out of my mouth randomly at the moment for some reason. Well, if we're able to compare the mechanical output power with the electrical input power, we're able to set or understand or track or monitor without having to pull anything apart. This can be has the option potential of being transmitted wirelessly. It could be something where we have alarms, just the red light goes boom when it says we've reached a threshold of inefficiency. That implies that we need to, within the next 2 months, get this rotary gear drive replaced, etc., etc., etc. But can we implement this CBM system after design phase? This is not a rhetorical question. How, if we come up with this idea after design phase, can we implement it? Yes or no, or any response in between? I agree with Asim. I also agree with Karen. Asim says no. Karen says at a cost. Evan says yes, but it is more difficult. Michael says it might be possible to add it during a maintenance operation. Yes. So it is possible, but costly. And as a rule, I've never seen this sort of thing get re-embedded after the design phase has happened, especially in the military context. In plants, this is much easier to implement. And when I say plants, you're talking about manufacturing plants, utilities, things like that, where you have a bunch of machines which are bolted to concrete, for lack of a better term, and you have a lot more access. They're usually a lot more expensive, those machines, and therefore the motivation to look after a single expensive machine is a lot higher. It's often a lot more cost effective to implement that for one of those single expensive machines. But if you have a fleet of 1,000 armored personnel carriers, each with 2 rotary gear drives, then you need to replace 2,000 rotary gear drive brackets. You need to then have cabling run to the controller. You then need to upgrade the software. You then need to go through the logistic information system to incorporate it, et cetera, et cetera, et cetera. So it is easy to say, yeah, you can do it during, some sort of scheduled downtime, but in practice, it's so much harder that it almost never happens. So let's move to another failure mechanism. Who has heard of an SN chart? Who has heard of an SN chart? SN chart. And this is... Anyone heard? At university, fair enough, yes. So an SN chart is a chart where we have S on the vertical axis, S stands for stress, and N on the horizontal axis, and N stands for number of cycles. And we use this for fatigue. And virtually every alloy has an SN chart, which has been well studied. And you can see here, this is the SN curve for 1045 steel. You notice that in the horizontal axis, number of cycles is scaled logarithmically. And all this line does is tell you how many cycles it will take for certain stress levels for your thing to fail due to fatigue. It just so happens that with steel, there's this thing called the endurance limit. So essentially for this steel, if the local stresses are below 300 megapascals, it will never fail due to fatigue. Fatigue is a slow growth of cracking over time. And often SN charts have confidence bounds or confidence intervals or confidence regions because it's not perfect. There will be some variations to the theme, but the concept remains fairly standard, fairly consistent. The idea is that you can use SN charts to work out the likely time or like how long your thing's going to take before it fails. And so fatigue, well, if you go into if you do a fault tree analysis or root cause analysis or FMEA and say, you know what, the shaft is actually going to fail due to fatigue. People say, okay, well, that's all. That is all about cracks growing over time. You can see here that, for example, if we have a 400 megapascal stress, then that might mean our shaft is going to take, in this case, 87,000 cycles before it's likely going to fail. That's a typical time to failure for our shaft. And we can even add a density curve like this to sort of incorporate the uncertainty we have in time to failure for our shaft. Now, if all of a sudden we're worried about fatigue on our shaft, why is fatigue a wear out failure mechanism for our rotary gear drive shaft? Why is it wearing out? William's asking questions similar to stress strength curve. Not quite. SN curve is not a stress strength curve. The SN curve literally maps stress to number of cycles. The stress strength curve has density curves for both stress and strength. So if we go back to this question, why is fatigue a wear out failure mechanism for the rotary gear drive shaft? Why is it wear out? Why would fatigue be wearing out? So I actually answered this a couple of times myself today, but we'll treat this as revision. Why is a fatigue failure mechanism a wear out failure mechanism? Crack growth is cycle based, which looks like wear out. Well, it is wear out because a metal has a memory. That is essentially, I think what you're getting at, Michael, is that the amount of damage that you inflict on a metal, i.e. the crack growth you incur for the first 3 months, will be ready to go for the last 3 months. It is accumulating damage or accumulating over time, i.e. accumulating damage over time, because its components have a limited life. You could argue that every component has a limited life, regardless of wear out, wear in, or anything in between. But essentially, anything that accumulates damage and fatigue, cracking, where the crack grows slowly, is a perfect example of the accumulation of damage. That makes it a wear out failure mechanism. Now, of course, we go, all right, well, that's all well and good. So wear out, then we can look at preventive maintenance and servicing and things like that. But let's throw one more curveball into our little thought bubble for today. Let's just say that if EMEA identifies that there is a chance that a fraction of rotary gear drive shafts will have manufacturing defects. You can see here are some example defects in the molecular lattice, or the atomic lattice, I should say, of the alloy. You've got impurities, vacancies, dislocations, substitutional atoms, grain boundaries. And these defects, what they do is they amplify the local stress. When we say amplify, what that means is that the local strength goes through the roof, which means that if there is going to be any cracking, it's going to start near these defects. Well, let's just further say that a process called highly accelerated stress testing, for example, identified that these defects will cause fatigue cracking. Now, these defects only exist in a small fraction of overall rotary gear drive shafts. So if we have fatigue, which we've just called wear out, but it's being triggered by defects that exist in a small population of the overall fleet, is this overall wear out or wear in or something entirely different? Sim says wear in. And I like it. Even though the thing is actually, in a very physical sense, failing due to a wear out failure mechanism, the fact that it is triggered by defects means that it will exhibit as wear in. And the idea is that what will happen is that after an arbitrary period of time, rotary gear drive shafts that don't have defects will simply stop failing due to fatigue. They'll eventually fail due to fatigue, but it's going to be an order of magnitude later on in the times of failure continuum. And so what that means is that even though we have a fatigue cracking or a wear out failure mechanism, we simply can't just use preventive maintenance or predictive maintenance to address this issue. We need to look at things that address manufacturing defects. Everyone asks, does it have to be one or the other? Well, it usually is, because wear out and wear in have very different statistical signatures or characteristics. The hazard rate is either going down or it's going up. And so It has to be one or the other. It's either going down or going up. It can't be both. But even though I've perhaps thrown a curveball your way by saying, hang on, a wear-out failure mechanism might exhibit as if it's wearing in if it's being triggered by defects in a small population of overall systems. So if that's the case, what might you be able to do in order to address situations associated with, or failures associated with fatigue triggered by manufacturing defects? What can we do? Material quality, continuous monitoring. Well, built-in testing. The reality with built-in testing is, again, that usually is associated with the accumulation of damage, which is a hallmark of wear out. Brad mentions get a better manufacturer, always a good one. Concur. Let's just say that review manufacturing process, which is along the same lines as Fred, is either like by substitution or improvement, get an improved manufacturing process. Let's just say though, you're concerned about these things as potential. What can you do as the operator, the user, the prime contractor? What can we do? Burn-in, right. Now, what is burn-in, David? Harry Smith. Nice read. So David's talking about this thing called burn-in testing. Inspect motors before wear-out, wear-in phase, and if they pass, I think, William, that's a sort of a it's a sort of hodgepodge of ideas in there. When you say inspect motors before wear out, wear in failure, well, and extend the replacement interval on good motors, that's mixing both condition-based maintenance and fixed interval maintenance. David Kinsey goes back to run-in, and that's essentially what burn-in means, or run-in means that you might get these motors from the manufacturer, and you put them on a test rig for a week or 2 weeks or however long. And when that happens, those motors which have those defects in the shaft are likely going to fail during that initial testing. And those without defects will pass with flying colors. And so the ones that fail during burn-in, you just don't use. They never get to your supplies or your spare parts store. Those that do are the ones you then use. Michael then pointed about X-ray the supplied shaft metal. Absolutely, that's a good idea. It's going to have to be subject to a cost-benefit analysis, and essentially, if the shaft is embedded within the actual the motor itself, that might be problematic. But that is one thing we can look at, is the whole idea of incoming inspection. First likely failure interval in lieu of burn-in test. I'm not sure what that means, William. I think there's a few ideas that are being combined in your responses that I don't completely understand, but I'm happy to explore those perhaps in our own time via email as well. ESS will not prevent failures, but will prevent potential units with limited life from being fielded. Yes, I'm talking about environmental stress screenings, which is different to burn-in, at least in some definitions, but the idea is you're trying to uncover or identify those units that have defects. Now, the main point of this is not to try and come up with an approach that will definitely work with the system, just trying to think about it. Now, if we don't think about it, then we'll come up with mandatory ideas and mandatory things. If we just say, hey, fatigue, damage accumulates, wear in, we'll just service. Preventive maintenance, inspection, done, move on to the next thing. If it's caused by manufacturing defects, then you need to have a completely different approach. It comes down to how you deal with things. But let's go back to that, to the whole idea of the failure mechanism associated with insulator breakdown. If we want to implement a corrective action like the one my FAMIA team came up with, It has to be designed into your system. You need to design supportability into your system. So how does supportability interact with reliability? In many cases, the technical interpretations of both definitions, they don't overlap. But in practice, reliability and supportability are all about understanding how your system fails and understanding it early so that you can incorporate things like monitoring the current draw versus mechanical or power output, incorporating sensors for built-in testing at the things that are going at the parts of the system that are going to keep you up at night. And the whole idea of just waiting to design something that can work as quickly as possible and then thinking about sprinkling supportability all over it, that has, I shouldn't say never worked, but it's just either one, unlikely to work, or two, if it is going to work, you need to spend a lot of money reinventing the wheel, so to speak, redesigning your system to have these sensors built in. Supportability has to be designed into your system. And when it comes to things like welding up the belly plate of an armored personnel carrier, if you don't think about these things from the very start, then you have ridiculous scenarios where the entire power pack needs to be taken out for you to change the oil, all because we didn't think about it early. Now, I understand that there is, we've just gone past the hour mark. I'm more than happy to hang around and answer questions. But for those of you who need to spear off and do something else, thank you for your time today. Hopefully you got something out of this. Please feel free to reach out to me if you have any further questions or want to talk about this any further. But if anyone's got any more questions, please feel free to write them, and I'll go through chats to see if I've missed anything. William writes, this is an example where accelerated stress screening may actually reduce the life of the shaft, or putting the shaft on a different place in the SN curve for accelerated stresses. That's always a risk. However, if you understand the fatigue characteristics well enough of, let's just say, defect-free steel, you will be able to understand how much life you lose from burn-in testing for good units, but you should also be able to work out how many defective units you will remove. And therefore, if a reliability engineer is good enough, they'll be able to work out whether it's worth it or not. Thank you, Evan, David, and Victor. No, not a problem at all. Thank you for joining us and asking questions. Thank you, Asim. And Sebastian, thank you. Lots of thanks. Feel free to, I need to hire a good metals person. Yeah, absolutely. Critical thinking is one of the most important ingredients for reliability and supportability. Thank you, Greg. And Michael, thank you.